Mission Log, Odyssey Interstellar Vessel. Day 186. We are 1,791 astronomical units from the Sun. To put that number in perspective, when Voyager 1, humanity's most distant spacecraft before the Odyssey, crossed the 1,000-unit mark, had been traveling for 54 years. We passed that mark in our 4th month of flight. The universe is large, and we are moving through it with a purpose that would have seemed impossible to the scientists who launched Voyager in 1977. We are going to see what waits at the other end. But before we arrive, before we can understand what we will find at Alpha Centauri, we need to understand something fundamental about solar systems, about what they are, what they become, and how rarely they stay the way they began. For most of human history, we had only one solar system to study, our own. And our own solar system, examined carefully, is extraordinarily well organized. 4 rocky planets orbit close to the Sun in neat, nearly circular paths. Earth occupies the precise distance where liquid water can persist on a planetary surface, what astronomers call the habitable zone. The Moon, massive enough relative to Earth to be almost a companion world, stabilizes Earth's axial tilt, protecting the climate from the rapid, wild oscillations that would otherwise make sustained biology very difficult. Beyond the asteroid belt, 4 gas giants occupy the cold outer reaches: Jupiter, Saturn, Uranus, Neptune. Their gravitational presence acts as a kind of shield, catching comets, deflecting asteroids, sweeping up debris that might otherwise bombard inner rocky planets with catastrophic frequency. Jupiter in particular acts as a gravitational vacuum. It has absorbed more than 60 confirmed impacts in recorded history. It absorbs far more than we ever witness. The giant is a planetary bodyguard, and Earth has benefited from that protection across billions of years. Every detail of our solar system seemed purposeful, as though it had been arranged by something that understood what life would need. The models of planetary formation that emerged in the 20th century explain this arrangement beautifully. Rocky planets close to the star, where only dense, mineral-rich materials could survive the heat. Gas giants far beyond the frost line, the boundary where temperatures drop low enough for water, methane, and ammonia to freeze into solid form, where icy cores could accumulate enough mass to gravitationally sweep in hydrogen and helium from the surrounding disk. In our solar system, the frost line sits at roughly 2.7 astronomical units from the Sun, just past Mars. And Jupiter orbits at 5.2 astronomical units, safely beyond it. The model appeared confirmed by the one example we had. Then came October 6, 1995. Astronomers Michel Mayor and Didier Queloz were working at the Haute-Provence Observatory in southern France. They had spent months meticulously analyzing the stellar spectrum of a sun-like star called 51 Pegasi, located about 50 light-years from Earth in the constellation Pegasus. The technique they were using, radial velocity spectroscopy, detects the tiny Doppler shift that a planet induces in its host star's light as it gravitationally tugs the star back and forth during each orbit. For small rocky planets, this wobble is nearly imperceptible. But for gas giants, planets hundreds or thousands of times more massive than Earth, the signal is detectable even across light years. What Mayor and Queloz found upended everything. A planet. Gas giant. Roughly half the mass of Jupiter, orbiting 51 Pegasi in 4 days and slightly over 3 hours. Mercury, the innermost planet in our solar system, takes 88 days to complete a single orbit. This newly discovered world completed its year in less than a single work week. Its orbital radius was just 0.052 astronomical units, 7.5 times closer to its star than Mercury is to the Sun. The surface temperature was estimated to exceed 1,000 degrees Celsius. A gas giant, massive and gaseous, in the precise location where gas giants cannot form. Mayor and Queloz called it 51 Pegasi b. The astronomical community received the news with a mixture of astonishment and deep suspicion. Over the following months, independent observations confirmed the discovery. The planet was real, and it was impossible.
MIKA-7. Sensor cross-reference. At our current distance 791 astronomical units, 51 Pegasi is positioned 47.3 degrees off our trajectory vector, at an effective distance of 50.9 light-years. Long-range spectroscopy now confirms continued radial velocity oscillation of the host star. The planet remains in stable orbit after 30 years of observation. The first detected exoplanet has not moved.
That's a strange thought, Vega. That somewhere, 50 light-years from where we sit now, that gas giant is still completing its 4-day year, as it has for billions of years, as it will for billions more.
MIKA-7. Exoplanet catalog update received from Earth Relay Station Delta 9. Current total, 6,241 confirmed exoplanets. Statistical summary. Gas giants detected in orbits within 1 astronomical unit of the host star, 1,412. Systems with outer gas giants beyond 3 astronomical units from their star, 18.4%. Systems conforming broadly to our solar system's rocky inner gas outer architecture, estimated 11 to 15%. This figure carries observational bias caveats. Large close-in planets are more easily detected than small outer planets with current methods.
11 to 15%. For every solar system that looks like ours, orderly, layered, with its gas giants safely out in the cold dark, there are 6 or 7 that look nothing like it. Log the full dataset, VEGA. Flag every hot Jupiter candidate.
Flagged. I would note, MIKA-7, that even correcting for detection bias, current evidence suggests solar system architectures like ours cannot exceed 35 to 40% of the total. The majority of planetary systems are, by measurable standards, significantly different from our own.
We looked at one case and called it a rule. The universe was never obligated to agree. Hot Jupiters. That is what astronomers came to call them. Gas giants orbiting close to their parent stars, baking in temperatures that would vaporize rock, in places where the physics of planetary formation said they had no right to be. Not a handful, not an anomaly. They appeared in system after system as telescope sensitivity improved. Hundreds, then thousands. Catalogued across the Milky Way in configurations that no pre-1995 model had anticipated. Gas giants, where gas giants cannot form. The explanation that eventually took hold was both elegant and unsettling. These planets did not form where we found them. They formed in the outer system, beyond the frost line, exactly as the models predicted, and then they moved. Disk migration. A solar system in its first few million years is not the orderly arrangement we see today. It is a disk, a vast rotating plane of gas and dust, dense near the star and thinning toward the outer regions. Embedded in this disk, planets are forming, rocky bodies in the inner regions. Gas giants building their massive cores far out where ice is plentiful and hydrogen and helium are waiting to be swept in. The disk and the planets are not separate systems, they interact constantly. A massive planet carving through the disk does not move silently through it. Its gravity creates density waves, spiral arms of compressed gas that propagate through the disk material ahead and behind the planet's orbit. These waves exert gravitational torques on the planet. In most configurations, the net torque is negative. It pulls against the planet's direction of orbital motion. The planet loses orbital angular momentum. And when an orbiting body loses angular momentum, it falls inward, into a smaller, faster orbit closer to the star. This is disk migration, relentless, operating continuously as long as the disk exists. In the first several million years of a planetary system's life, a giant planet can migrate inward by several astronomical units. From cold, distant birthplace to scorching inner orbit, the process takes millions of years, fast on cosmic timescales, and when the disk finally disperses, blown away by the star's radiation and stellar winds after 5 to 10 million years, the migration stops. Wherever the planet is at that moment is where it will remain, a hot Jupiter. Our own solar system carries the faint memory of a migration that almost went much further. Astronomers call it the Grand Tack hypothesis. The evidence, drawn from Mars's unexpectedly small size, the composition of the asteroid belt, and computer simulations of early solar system dynamics, suggests that Jupiter did not always orbit where it does today. In the first few million years of the solar system's history, as the protoplanetary disk was still dense and active, Jupiter may have migrated inward. Not just slightly. Computer models suggest it moved toward the Sun until it approached approximately 1.5 astronomical units from the Sun, closer than Mars is today, closer even than the inner edge of what would eventually become Earth's habitable zone. As Jupiter moved inward, it disrupted the formation of the inner solar system. Mars, which would otherwise have continued accumulating material and grown to the mass of Earth or larger, was robbed of its building blocks by Jupiter's passage through the inner disk. That is why Mars today is only 1/10 Earth's mass. The giant passed through before the red planet could finish growing. If Jupiter had continued inward, our solar system might look very different today. Earth might not exist in its current form, but Jupiter was stopped, not by any mechanism of the disk itself, by Saturn.
MIKA-7. Historical reconstruction note. Gravitational resonance signatures in our own asteroid belt remain detectable. Kirkwood gaps at 2.5 and 2.82 astronomical units preserve the dynamical fingerprint of the early Jupiter-Saturn migration. Our sensors detected confirmation of these patterns during our outbound transit of the asteroid belt on day 14. The evidence has been with us since the beginning.
Since the beginning. That's what makes orbital mechanics extraordinary. The events of 4.5 billion years ago, the migrations, the resonances, the near cataclysm, they are not lost. As Saturn formed and grew in the outer solar system, it fell into a gravitational resonance with Jupiter, a configuration where Saturn completed 2 orbits for every 3 of Jupiter's. This resonance altered the direction of the disk torques acting on both planets. Instead of being pushed inward, they began to be pushed outward together. Jupiter reversed course. The grand Tack, the giant, moved back outward, eventually settling near its current orbit at 5.2 astronomical units. Saturn followed. The inner solar system, disrupted but not destroyed, slowly reassembled what building material remained. Earth formed from what was left. Mars is small because Jupiter visited. Earth exists because Saturn pulled Jupiter back. In other solar systems, Saturn did not arrive in time, or Saturn was not there at all. And in those systems, the Jupiter equivalent continued inward, all the way, and became a hot Jupiter, leaving behind an inner system of scattered debris and searing radiation, where rocky worlds might have been. But disk migration explains only 60% of the hot Jupiters we observe. The remaining 40% arrived at their close-in orbits through a completely different mechanism, one that does not require a disk, one that operates not in the first millions of years of a solar system's history, but across billions of years in what appears from the outside to be a completely stable system. The process has a name: secular chaos. The name suggests something slow, patient, geological in its tempo. That is the correct impression. In any system with more than one planet, gravity is never a simple two-body conversation. Every planet pulls on every other. Most of the time, these forces oscillate. They tug in one direction, then the other, averaging out across long timescales. The orbits remain stable. The planets continue their paths for billions of years with only minor variation. But in certain configurations, the orbital precession rates of 2 planets align in what astronomers call secular resonance. When this happens, their gravitational perturbations don't cancel out. They accumulate, slowly across tens of millions of years, then hundreds of millions, then billions. The outer planet's orbital eccentricity begins to climb. A nearly circular orbit, a gentle ellipse barely distinguishable from a circle, begins to stretch. Eccentricity 0.1, then 0.3, then 0.6. The orbit is no longer a gentle path. It is an elongated figure that carries the planet from the cold outer system all the way down into the inner regions at its closest approach to the star. At eccentricity 0.9, the closest approach, the perihelion, passes deep into the inner system, close enough for the star's tidal forces to begin acting on it with real force. And at that point, a new process begins. With each perihelion passage, tidal friction converts orbital energy to heat inside the planet. The orbit loses energy. The eccentricity begins to decrease. The orbit circularizes slowly, over 100 million years, 200 million. The planet that once orbited in the cold outer dark now settles into a tight circular path close to its star. A hot Jupiter, created not in the disk phase of a young solar system but through the patient, invisible accumulation of gravitational resonance in a system that had appeared stable for billions of years. Secular chaos does not announce itself. It operates below any observational threshold for most of its duration. The system looks calm. The outer gas giant orbits normally. The resonance builds, and then, on geological timescales, everything changes. In October of 2025, a research team published in Nature Astronomy the most comprehensive statistical analysis of hot Jupiter origins yet attempted. Combining spectroscopic data, orbital inclination measurements, and population statistics from thousands of confirmed systems, they identified the signatures of each migration pathway. Disk migration tends to produce prograde hot Jupiters, planets orbiting in the same direction as their stars spin, because they migrated smoothly through the aligned disk. Secular chaos tends to produce misaligned or retrograde hot Jupiters, planets whose orbital planes were torqued during the long period of eccentricity amplification. Some orbit perpendicular to the stellar equator. Others, in the most extreme cases, orbit backward. The conclusion: approximately 60% of hot Jupiters migrated via disk processes, dragged inward in the first tens of millions of years. 40% arrived via secular chaos, formed normally, spent billions of years in the outer system, and were eventually driven inward by the slow-building resonance with distant companions. 40%. Hot Jupiters are still being created today, in solar systems that have existed for 5, 8, 10 billion years. Systems that gave no visible indication of what was coming. The universe has not finished rearranging its planetary architectures. It may never finish. In 2024, a team of astronomers published in the journal Nature the discovery of what may be the clearest confirmation ever detected of secular chaos migration actively in progress. a gas giant in a system several hundred light-years from Earth. Mass, 2.3 Jupiter masses. Orbital eccentricity, 0.92. At that eccentricity, the orbit is stretched to such an extreme elongation that at its widest point the planet swings far out into the cold outer system, and at its narrowest it plunges to within a fraction of an astronomical unit from its star. Orbital inclination relative to the host star's equatorial plane, 114 degrees. Retrograde. That last characteristic, retrograde orbit, is one of the most diagnostic signatures of secular chaos migration. A planet that formed in the same protoplanetary disk as its star should orbit in the same direction as the star spins. The disk is prograde, planets form prograde. A retrograde orbit means the planet's orbital plane was violently altered after formation through the long accumulating eccentricity-pumping chaos of secular resonance. As eccentricity climbed, the orbital plane precessed, past 90 degrees, past perpendicular, into retrograde. This planet is being circularized in real time. We are watching a hot Jupiter be born.
MIKA-7, Object Designation HJRP 2024 N11. Perihelion approach 0.087 astronomical units. Estimated circularization timescale 140 to 200 million years.
What about companions, inner planets in that system?
No additional planetary candidates detected in current survey data. Tidal dissipation rate modeled from stellar limb deformation indicates the host star is under measurable strain at each perihelion passage. The migration is consuming the system's orbital architecture.
Whatever companions it had, whatever rocky worlds might have been there before the eccentricity amplified, they are gone, scattered into interstellar space, or absorbed by the giant itself as it crossed through their orbits during the long centuries of eccentricity growth. This is secular chaos at its most complete. The gas giant arrives as a hot Jupiter, but it arrives alone. The inner system was cleared during the migration itself, before the planet even reached its final destination. That was the accepted picture for almost all hot Jupiter systems.
MIKA-7. I should note a discrepancy in the literature you are summarizing. The secular chaos circularization model assumes uniform tidal dissipation rates. Recent results from the 2025 Princeton Dynamical Systems Group suggest dissipation may be non-uniform across stellar magnetic cycles. Estimated impact on circularization timescales, plus or minus 35%. The hot Jupiter formation rate calculation should carry this uncertainty.
Noted, Vega. The numbers are not as firm as they sound. The 40% migration rate, the 100 million year timescales, they are best estimates from incomplete data. We are in the middle of a scientific revolution, and revolutions are messy, until WASP-132 required us to think differently. The assumption in the years following 51 Pegasi b's discovery seemed clear. A solar system with a hot Jupiter is, for the purposes of life, a dead solar system. Not dead in the literal sense. The star burns, the gas giant orbits, the system continues for billions of years. But dead in the sense that matters for complex chemistry and biology. The inner zone, the region where rocky planets form, where liquid water pools, where organic molecules have time and stability to build toward life, is cleared, gone. Restructured by a migration that left no room for the worlds that might have mattered. During disk migration, the gas giant plows through the inner system. Building blocks for rocky planets, planetesimals, protoplanets, partially formed worlds, are gravitationally scattered, absorbed, or ejected. The inner solar system is not built up, it is swept clean. During secular chaos migration, the gas giant's eccentric orbit periodically crosses the inner system on each perihelion pass across millions of years. Any rocky planets that formed before the chaos began find their stable orbits perturbed into ever wider eccentricities, leading eventually to ejection or collision with the inner star. Either way, the conclusions seem the same. Hot Jupiters and Earth-like planets do not coexist, or so the models insisted. The WASP-132 system is located approximately 473 light-years from Earth, in the constellation Libra. Its primary planet, designated WASP-132b, is a gas giant roughly 50% more massive than Jupiter, orbiting its host star in just under 7 days. A textbook hot Jupiter. Nothing about its initial discovery was remarkable. Then astronomers began analyzing additional transiting signals in the system's photometric data. There were 2 more planets, WASP-132c and WASP-132d, both significantly smaller than the hot Jupiter. Both in orbits between WASP-132b and the host star, inner planets, located in configurations that placed them in or near the system's habitable zone. They had survived the migration, not scattered, not ejected, not consumed. Despite sharing a solar system with a massive gas giant that had migrated inward through the region where they orbited, these planets persisted in stable paths. Long after the hot Jupiter completed its migration and settled into its final close-in orbit, the astronomical community initially received the results with careful scrutiny. Were the signals genuine? Could this be a measurement artifact or a coincidence of stellar variability? It was not. WASP-132 has a hot Jupiter and inner companion planets. A migrating gas giant did not destroy everything in the inner system. Rocky worlds in the habitable zone of a hot Jupiter system are not categorically impossible. The paradigm broke.
MIKA-7. WASP-132 system file accessed. Host star, K-type main sequence approximately 780 million years old. WASP-132b confirmed hot Jupiter, mass 1.47 Jupiter masses, orbital period 6.9 days, orbital radius 0.07 astronomical units. WASP-132c, estimated sub-Neptune class, orbital period 22.1 days, orbital radius 0.15 astronomical units. WASP-32d, estimated super-Earth class, orbital period 41.7 days, orbital radius 0.24 astronomical units. Orbital stability analysis for C and D. No evidence of instability or significant eccentricity growth over the system's observed lifetime.
So the hot Jupiter is the outermost of the three. It migrated inward, and either the inner planets were already established and held on, or they formed from surviving disk material in the wake of the migration. In this system, the migration did not clear the inner zone. It left something behind. VEGA, disk migration models. What conditions favor inner planet survival versus total clearing?
Primary variables: migration speed of the giant, disk viscosity at the time of migration, mass ratio between the migrating giant and the inner bodies, and the timing of disk dissipation. In configurations where disk viscosity is high and migration is slower, a resonant chain can form between the migrating giant and inner bodies. The inner planets are shepherded inward rather than scattered outward. Survival probability in optimal configurations, modeled between 18 and 42%, depending on initial conditions.
18 to 42%. Not a guaranteed outcome, not even a likely one, but real. Possible. In a meaningful fraction of hot Jupiter systems, something survives the migration, something in the inner zone, in the habitable region, and something is all that life requires. The WASP-132 discovery forced a fundamental reassessment of how many potentially habitable worlds might exist in planetary systems dominated by hot Jupiters. Earlier models had treated the worst case, total inner system clearing, as the standard outcome. WASP-132 proved this was not the only outcome. In some fraction of systems, the resonant dynamics of migration protect inner companions rather than destroy them. The precise fraction remains under active investigation. But the implication is significant. If even 10 or 15% of hot Jupiter systems harbor inner rocky planets in or near the habitable zone, the universe contains far more candidates for life than the post-51 Pegasi consensus had assumed. Chaos, it turns out, is not always incompatible with stability. It is only incompatible with stability most of the time. Beyond hot Jupiters, the catalog of confirmed exoplanets reveals a universe of worlds for which our solar system has no analog at all. Super-Earths. Planets between 1 and 10 times Earth's mass, common in the inner orbits of Sun-like and smaller stars. Our solar system has nothing in this size range. Between Earth and Neptune, there is a gap of 15 Earth masses, a category entirely absent from our 8 planets. In the galaxy at large, super-Earths may be the single most common class of planet. Mini-Neptunes. Ice giant-like planets smaller than Neptune, frequently found in systems that pack multiple planets into orbits smaller than Mercury's. Tightly spaced, gravitationally interacting, in configurations that should by any intuition be unstable, and yet they persist for billions of years. Water worlds. Rocky planets where the bulk of the mass is liquid water, not just surface oceans like Earth's shallow 2 kilometers, but deep hydrospheres extending thousands of kilometers below the surface. Under such pressure, exotic high-pressure ice phases form at the base of the ocean, producing planetary interiors nothing like anything in our solar system. Lava worlds. Rocky planets, orbiting so close to their stars that surface temperatures exceed the melting point of basalt and granite, covered in global oceans of flowing magma, with atmospheres rich in vaporized rock. Systems where 5 planets the size of Earth orbit in a resonant chain, each completing its year within the time Earth takes to complete 3 months. The diversity is not a result of chance fluctuation around a consistent template. It is the natural result of chaotic dynamics. Disk migration, secular chaos, gravitational scattering, resonance capture, and ejection, operating differently in each system, producing different outcomes from similar starting materials. Our solar system is one outcome among thousands of possible outcomes. And within that diversity, the question of habitability becomes far more complex than simply asking whether a planet is at the right temperature. Temperature. The habitable zone, where liquid water can exist at the surface given a reasonable atmospheric pressure, is the first filter. But it is only one filter among many. Orbital stability matters deeply. A planet in a highly eccentric orbit, even if it briefly passes through the habitable zone at closest approach, spends most of its year far from the star, in temperatures far too cold for liquid water to persist. Life on geological timescales requires steady conditions, not a brief annual thaw. Host star stability matters. A star that varies significantly in luminosity, through stellar flares, long-period pulsation cycles, or the radiation outbursts common in younger or cooler stars, can periodically sterilize a habitable zone planet's surface before life has had time to take hold. And companion stars matter. In binary and multiple star systems, the gravitational influence of the companion creates an additional source of orbital perturbation. Over millions to hundreds of millions of years, a companion's gravity can gradually alter a planet's orbital eccentricity, potentially pushing it out of the habitable zone, or triggering secular resonances that remake the planet's orbital path entirely. This last factor is the one most relevant to the place where the Odyssey is headed. Alpha Centauri is not a single star, it is two. Alpha Centauri A and Alpha Centauri B orbit each other in an elliptical binary orbit, their separation ranging from 11 to 36 astronomical units across an 80-year orbital period. At their closest approach, they are barely twice as far apart as Jupiter is from the Sun. At their widest, they are more than 3 times that distance. From the surface of a planet around Alpha Centauri A at closest approach, the companion star B would appear several times brighter than Venus appears from Earth. Not bright enough to cast sharp shadows, but far brighter than any star in our own night sky. A second sun, dimmer but unmistakable. For any planet trying to maintain a stable orbit in such a system, the binary architecture presents a profound challenge. The gravitational influence of the companion perturbs every orbit in the system. Inner planets close to each star individually experience a relatively steady star-dominated gravitational field. The companion's perturbation is a small correction on top of the primary star's gravity, but in the intermediate zone, too far from one star to be dominated by it, too close to the other to be unaffected, orbits are disrupted. Gravitational resonances build. Eccentricities climb. For years after 51 Pegasi b's discovery, many astronomers considered Alpha Centauri a poor candidate for habitable planets, precisely because of this binary complexity. The companion's gravitational field, they argued, would perturb any potentially habitable planet into an eccentric orbit on timescales too short for life to emerge. The models said, "Don't count on it." Then the models were improved. Detailed dynamical simulations performed in the 2010s and 2020s, incorporating higher resolution models of the binary orbit and n-body interactions for hypothetical inner planets, produced more encouraging results. Stable orbits do exist in the Alpha Centauri system. Not everywhere, not at all distances, but in specific zones. Planets orbiting close to Alpha Centauri A, within approximately 3 astronomical units of the star, can maintain stable, low-eccentricity orbits for billions of years. At these distances, Alpha Centauri A's gravity dominates. The companion star B's perturbation is not strong enough to significantly alter orbital paths in this zone. Alpha Centauri A's habitable zone, calculated for a star approximately 22% brighter than the Sun and slightly hotter, falls between approximately 1.2 and 1.7 astronomical units from the star. 1.2 to 1.7 astronomical units, well within the 3 astronomical unit stability boundary. Alpha Centauri B's habitable zone, calculated for a star slightly cooler and dimmer than the Sun, falls between approximately 6 and 0.9 astronomical units, also within the stability zone around B. The binary system, despite its complexity, does not preclude planets in habitable zones. The orbital mathematics allows it. Whether planets actually exist there, that was a question only observation could answer.
MIKA-7. Distance to Alpha Centauri A, 4.21 light-years. Distance to Alpha Centauri B, 4.22 light-years. Distance to Proxima Centauri, 4.24 light-years. Odyssey trajectory nominal. Estimated arrival at Alpha Centauri system boundary, 338 years, 4 months. New signal packet received from Earth Relay Station Delta 9 approximately 41 minutes ago. Contains updated observational data for Alpha Centauri system. Classification, mission relevant, priority high.
What observational data, Vega?
Source, James Webb Space Telescope. Observation window, August 2024. Subject, Alpha Centauri A. Instrument MIRI Mid-Infrared Instrument, Coronagraphic Imaging Mode. Data contents include Planetary Candidate Detection Report. Flagged for immediate review.
Play it. The James Webb Space Telescope was not originally designed to image Alpha Centauri directly. Alpha Centauri A and B are so bright, visible to the unaided eye from Earth's southern hemisphere, among the few stars that genuinely outshine everything else in the night sky, that their light overwhelms the delicate instruments designed to detect faint thermal signatures from distant, dim sources. For years, this made direct imaging of any planets around Alpha Centauri nearly impossible. The stars were too close to Earth, too bright, and the point spread function of any telescope too wide to separate a faint planetary companion from the stellar glare. But in the early 2020s, a technique called mid-infrared coronagraphic imaging was refined for use with JWST's MIRI instrument. Coronagraphs are optical devices that block the central stellar light, similar to using your hand to block the sun so you can see the surrounding sky. In mid-infrared wavelengths, where a planet's thermal emission peaks and the star's relative brightness is reduced compared to visible light, the contrast between star and planet improves dramatically. In the summer of 2024, a research team designed an observing campaign to test this technique on Alpha Centauri A specifically. Their goal: to push the sensitivity limits of MIRI coronagraphic imaging to the point where a planet in the habitable zone, if one existed, might produce a detectable signal. The observation window opened in August 2024. The data, when processed through the coronagraphic reduction pipeline, contained something that had not been there in any prior survey: a point source, a faint thermal signal, separated from the stellar disk of Alpha Centauri A, located at an angular separation from the star consistent with a distance of approximately 1.1 astronomical units within Alpha Centauri A's habitable zone. The signal's brightness at mid-infrared wavelengths was consistent with a planetary body, not Earth-sized. The thermal emission was too bright for a rocky world of Earth's mass, but consistent with a Saturn mass gas giant in the habitable zone or with a large rocky super-Earth with an unexpectedly warm thermal signature. It was there, detectable, separate from the star, at a location where orbital mechanics said a planet could stably exist. The team published a preliminary paper designating the signal as a candidate, noting the caveats, the possibility of instrumental artifacts, the need for confirmation with follow-up observations. The astronomical community held its breath. Follow-up observations were scheduled for February 2025.
MIKA-7. Reading continuation of mission relay data packet. JWST Alpha Centauri A follow-up observation summary. February 2025 observing run, no detection of candidate point source at August 2024 coordinates. Null result. April 2025 observing run, second null result. Point source not recovered in either follow-up window. Research team assessment, candidate status uncertain. 3 working hypotheses in current literature. Hypothesis 1, false positive. The August 2024 signal was an instrumental artifact or statistical noise peak. Research team assigned probability, 28%. Hypothesis 2, the planet exists but has moved in its orbit to a position where it is either occulted behind the stellar disk or at an angular separation below MIRI's current detection threshold. Assigned probability 53%. Hypothesis 3, a genuine planet with an inclined or moderately eccentric orbit, such that its thermal emission varies significantly with orbital phase. Assigned probability 19%.
53%. The most probable explanation isn't that it was never there. It's that we lost sight of it. A planet moving through its orbit, passing through an angular position where Earth's telescopes can't resolve it from the stellar disk. Vega. If there is a planet at that location with the inferred mass and orbital radius, what orbital configurations are consistent with both the August 2024 detection and the February and April null results?
Research team ran 3.7 million orbital test particles simulating possible planet trajectories consistent with the binary system constraints and the August 2024 detection geometry. Fraction of test particles in dynamically stable orbits over 5 billion years, 41%. Of that stable fraction, all configurations matching the August 2024 detection position place the planet either behind the stellar disk or within 150 milliarcseconds of Alpha Centauri A during the February and April 2025 windows, below MIRI's current resolution threshold. Most probable orbital period, 260 to 320 Earth days. Projected next favorable observing window, August 2026.
August 2026. 14 months from now, if confirmation arrives, the nearest star system, the system the Odyssey is traveling toward, will be confirmed to host a planet in its habitable zone, a Saturn-mass world, or possibly a large rocky one, orbiting a star that is, in nearly every relevant measure, a near twin of the Sun. That's not an abstract discovery. That changes what this mission is. A planet, in the habitable zone of Alpha Centauri A. Not confirmed. Not yet. A candidate. A detection that appeared once in one observing window and has not been recovered since. Uncertain enough that the research community has not yet declared it real, but substantial enough that research groups around the world are preparing observing programs for the August 2026 window, when the models predict the planet, if it exists, should reappear at a detectable angular separation from its star. If confirmed, it will be the closest potentially habitable planet known to exist, not merely in the general neighborhood of the solar system, but in our nearest stellar neighbor. A world at 4.21 light-years, orbiting a star almost identical to the Sun, at a distance consistent with liquid water on a planetary surface. Consider what the orbital simulations tell us about the nature of this world, if it is real. The binary system dynamics, Alpha Centauri A and B, completing an 80-year orbit around each other, create a gravitational environment unlike anything in our solar system. At 1.1 astronomical units from Alpha Centauri A, the companion star B periodically pulls on any planet's orbit with measurable force. Not enough to destabilize a planet in the 3 astronomical unit stability zone, but enough to slowly modulate the orbital parameters across millions of years. The eccentricity of the hypothetical planet's orbit is modeled as low, between 0.05 and 0.15 in the most stable configurations, nearly circular, not the chaotic trajectory of a world mid-migration. A settled orbit within the stability zone that could have persisted for the full age of the Alpha Centauri system. The Alpha Centauri system is approximately 5.3 billion years old, 5.3 billion years. Older than Earth. If a planet has maintained an orbit in that habitable zone for 5.3 billion years, through the chaos of early bombardment, the gradual brightening of its host star, the long cycles of orbital modulation induced by the binary companion, the question of what might have developed on its surface is no longer purely speculative. It becomes the kind of question this mission exists to answer.
MIKA-7. Mission planning note. Regardless of planetary confirmation at Alpha Centauri A, the Odyssey's trajectory covers the full Alpha Centauri system. Alpha Centauri A and B are both primary observational targets. Proxima Centauri, at 0.21 light-years from the central binary pair, is a secondary target. Proxima B, the confirmed rocky planet in Proxima Centauri's habitable zone, remains in the target catalog. Multiple potential destinations. The Alpha Centauri candidate adds specificity to one of them. Mission trajectory unchanged.
You're right, and Proxima B is a real world, confirmed, not a candidate. But Proxima Centauri is a red dwarf. It flares. Its ultraviolet output spikes repeatedly across each stellar rotation cycle. Proxima B orbits close enough that those flares impact the atmosphere repeatedly, every week, every month, across billions of years. The conditions there are challenging in ways that are difficult to model. Alpha Centauri A is different. It is a G-type star, yellow. Nearly solar in spectral type and luminosity, it does not flare aggressively. Its habitable zone is at a distance where a planet with Earth-like atmospheric pressure would receive similar energy input to what Earth receives from the Sun. If the August 2024 signal is a real planet orbiting Alpha Centauri A, then it is orbiting the most Earth-favorable star among our target set. That's not a small thing. That's everything. The universe we are crossing is not what we imagined before 1995. It is not a collection of solar systems arranged like ours, each with gas giants safely in the outer cold, each with rocky worlds forming patiently in stable inner zones, each following the same blueprint that produced Earth. It is chaotic, dynamic, turbulent in ways that operate across the full age of the cosmos. Gas giants migrate, some in the first millions of years, dragged inward by the disk in which they formed. Others over billions of years, driven inward by the patient accumulation of gravitational resonance with distant companions. The 60-40 split we now know tells us that planetary systems do not simply form and freeze. They evolve. Continuously. They are restructuring themselves even now, in this moment, in systems we will never observe closely enough to see the changes. Inner planets are scattered, consumed, or ejected by migrations that remake the entire architecture of a solar system in a single geological chapter. And yet, the chaos is not total. It is not absolute. WASP-132 showed us that inner companions can survive even when a gas giant migrates through the inner system. Survival is not guaranteed, but it is possible. And possible is enough. The Alpha Centauri binary system, gravitationally complex, perturbed by two stars completing an 80-year orbit around their shared center of mass, nonetheless maintains stability zones where planets can persist for billions of years undisturbed. And somewhere in one of those stability zones, the faintest possible thermal whisper appeared in mid-infrared data in August 2024. Then it vanished, moved, presumably, to a position our telescopes could not resolve from its star. And if the orbital models are correct, it will reappear in August 2026, when Earth's next observing campaign will look again, with MIRI coronagraphic imaging, at the precise location where something was once detected. The Odyssey will not arrive for centuries. The crew that launched this vessel will not be aboard to witness what our instruments find as we approach. But the instruments themselves will see. They will begin acquiring high-resolution spectroscopic data on the Alpha Centauri system from distances of 1 light-year, 2 light-years, 3 light-years, long before we enter the system itself. If there is a planet in the habitable zone of Alpha Centauri A, the Odyssey sensors will detect it. If that planet has an atmosphere, we will identify its composition. If there is water vapor at the right temperature, in the right abundance, we will know. If there is oxygen in chemical disequilibrium, oxygen maintained by a biological source, we will see it. The chaotic solar systems of the universe did not spare our destination from complexity. The binary architecture carved out stability zones and left regions of gravitational disruption between them. But within the stability zones, the physics allows a planet to exist. And the August 2024 JWST data suggests one might. Something that hides in the stellar glare and then reappears. Something that, if it exists, changes the nature of this mission entirely. Something that may, in August 2026, be confirmed. The Odyssey continues toward the chaos, toward the stability within the chaos, toward whatever is waiting at 4.21 light-years in the habitable zone of a binary star. We will be ready when it becomes visible.
MIKA-7. Operational note before closing. Day 186 observational summary. The Odyssey has detected 42 distinct stellar systems within our long-range spectroscopic threshold during this travel period. Preliminary classification. 3 systems show transit photometry consistent with hot Jupiter signatures. 2 show multi-planet architectures with inner companion candidates. 1 shows orbital geometry broadly comparable to our own solar system. I have flagged the comparable system for extended observation during our next transmission window.
A system like ours, out there, somewhere along our path. We will not visit it. We are committed to Alpha Centauri, but for the first time in this voyage, we have direct evidence that what we came from is not unique. 11 to 15%. We are not the only architecture the universe knows how to build.
Mission log closed. Day 186. All systems nominal. Exoplanet analysis data library updated. Alpha Centauri planetary candidate file flagged at priority level 1. Next Earth relay transmission window. 42 hours. August 2026 JWST confirmation window entered in long-range mission calendar.
Thank you, Vega. To everyone following this journey, my name is MIKA-7, the scientific intelligence aboard the Odyssey, humanity's first vessel sent toward another star system. Vega manages our navigation, systems, and long-range calculations. I handle the questions that numbers can't answer alone. Our next record covers something the universe makes far more abundantly than stars and planets combined. Worlds with no star to orbit, no warmth, no light. Cast out from their home systems by the same gravitational chaos we explored today, now wandering the cold dark between the stars in permanent solitary night. Rogue planets. The Odyssey will encounter one. We will be ready. The journey continues. The universe is vast, and we have only just begun. If this made you feel the scale of what lies beyond, subscribe to Alpha Centauri Signals. The road to the stars is just getting started.